Now, what's really nice about this, and one of the reasons that we're going into it right now, is because a lot of the stuff that you learn and build in chapter 14 is going to be continue to be used in chapter 15. We got to clean it up a little bit. All right. Do you guys remember when we used the addition rule? The addition rule when you had or, when we used addition. What did that assume about those two events? That they were disjoint, that if one happened, the other couldn't. So we have to have a new rule, all right, the new rule that allows us to continue to add, but even when the events are not disjoint. Same thing for multiplication, all right? Multiplication of just multiplying for and, we assume that the events were independent. But what if they're not? All right, so I'm going to show you a new formula for that as well. All right, so here's the new addition rule. You can see the first one we used, which was just adding the probability of event A plus the probability of event B. But if the two events are not disjoint, then we must use this one. All right, so I'm going to help you guys use that today in an example, which starts off exactly the same, but you have to subtract out the probability of A and B. So I'll write that down for you. This is the probability of A and B. All right. You're going to see in an example we do that we have to do this or we'll be double counting. Okay? We'll be double counting. We don't want to double count. Any questions so far about the new way we're going to add with or? Yes, question. The difference is that you didn't have this before, right? This wasn't here because our two events were disjoint. So the probability of A and B happening, if they're disjoint, is 0, right? They'll never happen together. It's still equal to the same thing, but it's going to give us a different number when we're working with the problems. Mr. Brenner? Yes. I do. Yes, can I send them at the end of the class? Awesome, thank you. You got it. Stop calling me. All right. Edgar, at the end of the day, go to corporate study. Right. Tell him I sent you. Okay. No, because he wants to learn. Right, Edgar? Let's stay. Let's do it. So, I don't know if that... go again? Yes? No? So you're asking what's the difference? The difference is that before, we were cool with this one because the events we always used could never happen at the same time. That's not always the case, right? We want to find out the probability that this event or that event could happen, but they both could happen at the same time. So that's why I have to add in this, and I'll show you later why that's important. Okay? All right. The conditional probability. All right, this is an important one. It's another notation. It's right here. I'll write it a little bit bigger. So whenever you see this vertical line, when you're working with probability, that means given. All right, given. G-I-V-E-N. Given. All right, so the way you read this is the probability that event B happens given event A has already happened. All right, so conditional probability means that an event has already occurred. All right, so if I tell you that event A has already happened, what's the likelihood that event B also happens? All right, there's a formula for that too. Don't worry, you don't have to memorize this one. Oh, I went the wrong way. Here it is. Here's the formula. Okay, so this is called a conditional probability. Again, you do not have to memorize this formula. You do need to know how to use it, obviously. So you'll notice the denominator is always the given. I want your brains to see this because all of you guys have great brains. The given, so after the bar, is always in the denominator. The probability of your given happening goes in the bottom. All right. Now look what's in the numerator. Do you know what that is? That's the probability of A and B happening in the numerator. The probability of A and B happening in the numerator. All right? Now, the reason we do that is because if A already happened, right, which is our given, and I want to know the likelihood that B is going to happen, well, then I have to do them at the same time. A and B. You could write B and A. It doesn't matter, all right, because A has already happened. All right, so I get a lot of students every year that want to write the probability of B over the probability of A for this, all right? But the problem is that B and A has to be in the numerator because A has already happened, all right? So that's why it's not that. Okay, now I told you guys the multiplication one's going to have to change. What's nice about this one is that it's just this form up here for conditional, just rearranged, all right? So if you look over here, you'll see all they did was they rearranged the conditional formula. All right, I'll give you an example. So it was this. All right, so if you solve for this one, you just move this one over, the probability of A over with multiplication. So that's how they get that. All right, that's just algebra. Okay, so you don't have to memorize like another formula. You just have to use the conditional probability and try to find what's missing. Okay, now, independence. We already talked about independence. Who remembers what independence means? You had to write it down on your quiz. Who remembers what independent events, what does that mean when I say two events are independent of each other? Can you... Results? Right? I liked yours, David, but there wasn't much to it. Right? Say yours again. Say it again.
The effects will never affect the other event.
Great. I agree. I would go a little bit further and say if one event happens, the likelihood of the other event happening is unchanged. It's the same. All right, and I always think of that example of an event happening across the Atlantic Ocean and an event happening in Houston. The likelihood of those events having an impact on each other is low. All right, that's why we say they're independent. Right, the weather in Germany does not affect what's happening here. All right, now there's actually a mathematical way to prove this. All right, and we're going to prove this today. Maybe not today, actually. Nope, yep, we're definitely going to do it today. We're going to mathematically prove if two events are independent or not. Okay? So I'll show you how to do that and really get your brain going at the end of a long week. Are we done yet? Nope, not done. Now, who remembers disjoint? Who remembers disjoint? Or mutually exclusive? I'll take that this time, David. If one happens, the other one actually cannot happen. All right? So if one happens, the other one can't. That means they are mutually exclusive or disjoint events. All right, we'll do like 3 examples today to kind of talk about all of this together. Are they disjoint? Are they independent? Are they neither? Right? I get every year, I'm like, students will say, oh, it's not disjoint, it must be independent. No, you can have neither. Okay? So don't just assume it's one or the other. This thing I put at the bottom here, just to remind you from middle school days, that when it says without replacement, they don't put it back in the pool or wherever it was in the bag. All right? So if it says with replacement, they're putting it back. Right? I always think about when I have my M&Ms, that's without replacement. You're eating them? You're not replacing it? No? Just me then. I bet Liam at home is going to love that one. All right. Now, this thing, tree diagram, we're not going to get to it today. All right, we'll get to it on Tuesday. But it's kind of a behemoth, all right? Especially the first time you do one, you get a little bit overwhelmed. It's a lot of work to then do what you think is like, well, that's not that much from all that work. So we'll do a lot of examples with tree diagrams. And the hardest part is when I give you guys the test is to get your brain to recognize, oh, that's a tree diagram they want me to make. Right? When I read a problem, my brain immediately goes to, they want me to make a tree diagram. So I'm going to do my best to try to train your brain to recognize when you want to make a tree diagram. All right? They're really cool and they're very helpful, but they do take a little bit of work. All right? Okay, questions before we do one. Not a tree diagram, but do a problem together. Been waiting all day for this. Whew. We ready? No? What are you scared of? We already took the quiz. Everybody good? I'm sorry? the grade hidden in the grade book. Well, I'm not going to grade it today. I'm definitely not grading over the weekend. So you got many days to enjoy it. All right. Let's do this example. All right. Now, this example was a lot more relevant 8 years ago when I first started using it. All right, because a lot of kids still play cards. But I'm not. You still play cards? Yeah. Oh, really? Oh, most kids are like, what is that? Well, I'm just telling you, I've had kids that are like, what are those? So it's all good. If you've never played cards, or maybe you play it on your phone, that's fine. It's the same thing. So all of these questions are going to talk about a deck of cards. All right, and just letting you know, on the test, there's going to be questions about a deck of cards. You want to get your brain used to this? Maybe over the weekend, go to Walgreens, get a deck of cards, play some cards. Yes. Oh, the test before the midterm on probability. Right before the midterm.
We have a test before. We have a test and a midterm.
Absolutely. That's how it works. No, it's not. It's just a unit test. It's just a test.
It's a pretest, a big test.
Nope. It's the same as we've always had. It's gonna be great. You're gonna be fine. All right. So let's do this together. We're going to do these 2 slides together, and we'll be done. We'll leave. All right, if it's before 4:03, we'll wait till 4:03. So we have 52 cards. All right? So if you've ever seen a deck of cards, there are 52 cards. All right? If somebody asks you to play 52 pickup, just say no. All right, so we draw a card. Draw a card. I might have a deck of cards. Oh, where's my cards? Not here. Sad. Oh! Come on, cards. Nope. They're gone. I used to have them. Anyway, you draw draw a card. Okay? 1 card is drawn. What is the probability that it is an ace or it's red? An ace is just it has the little A. Thank you. I mean, that's all it is. So the way the card is, you have all the numbers 2 through 10. 2, 3, 4, 5, 6, 7, 8, 9, 10. And you have one of each of these suits. Okay? Then you also have Jack, Queen, King, which are called face cards because they have faces on them. And then you have 4 aces, which sometimes in some games they count as 1. Some games they count as 10 or 11, depending on the game. Yes, diamonds and hearts are red. Spades and clubs are black. All right? Okay, so let's see if we can do this. If we're using the formula from chapter 14, you see the word or, so what are you going to do? You're going to add them. So the probability of an ace plus the probability of a red card. All right, so let's do the aces first. I think I heard, well, let's just do 52 for now. There's 52 cards. How many are aces? 4 of them. There are 4 aces out of 52 cards. Okay? How many out of 52 cards are red? It's 26, actually. 13 and 13. They're in the 13. You're good. So 13 red hearts, 13 red diamonds. That's how I got 26. Hold on. Aces are in there. Aces are in there. Promise. Now, here's the problem, guys. All right, and Leslie F., this is what I'm hoping you'll understand. You good? All right, this is what I'm hoping you'll see. If we just stopped and said, this is our answer, 30 over 52, whatever that is, it's wrong. Why is it wrong, David?
There's 12 on both sides.
Ah, yes. In this one, we have the red ace of hearts and the red. Oh, is that what you're saying? Oh. I thought you were trying to say this was 28. You try to say the answer is 28. My bad, I didn't know you were going to. So we have to subtract. Remember that formula you just took notes on? Subtract the probability of an ace and a red card. All right, so that's why I have to subtract that out. So I'm going to subtract 2 over 52 because there are 2 aces that are red. Okay, Leslie F., did that help or no? Okay, great. All right, so the answer is 28 over 52. All right, and for today, for this example, we're just going to leave it as a fraction. But if you wanted to get a decimal, obviously you could. Question? Okay. Yes, Bianca.
So you're just supposed to know, like, which two red aces.
Yeah, I mean, again, this example was great when my kids played cards, but not everyone plays cards. So I'll try to get a couple of decks of cards, and then we play some card games. Yes. The formula, yeah, so the formula is the probability of event A or B, listen, is probability of A plus the probability of B minus the probability of A and B. And this one you do not need to memorize. I'm going to give it to you. Okay? Yes, Michelle. No. Okay. Okay, number two. Number two. Two cards are drawn without replacement.
So those are 50 cards.
Hold on. So without replacement means when I draw it, I don't put it back with the other 52 cards. So I'm taking it away from that pile. So it says, what's the probability that the first card I get is an ace and the second card is an ace? All right? So when I haven't drawn a card yet, how many cards are there? 52. And how many aces are in that deck? 4. But when I multiply to get the second one, I've already pulled one card. So now there's 51. And, David, I pulled an ace. So now there's only 3 aces left. So that's it. They just want me to pull 2. All right? So whatever that is. I'm not even going to write it down. You guys got it. Can you get it for me? Use N over D, and it'll reduce it for you. Use N over D. Winston, go faster than that. That's what that does. So you type in fractions. Yes way. No cap. What'd you get?
0.004.
I wanted the fraction, man.
Oh, my bad. 1 over 2021.
That's helpful, right? Basically, is that going to happen? Probably not.
Yes.
Probably not. Let's do number 3. Everybody go to number 2?
Yes.
What just happened? We did number 2.
Yeah.
We drew an ace, put it to the side, we drew another ace, Lily J.
Okay.
And that was really lucky because 1 out of 221 is not likely to happen. All right, number 3. I draw a card and I look at it and I tell you it's red. Okay? What's the likelihood that it's a heart? So this problem is screaming at me to do a conditional probability. What is the given? What is the given? What am I telling you? I'm telling you that it's red. All right? And if I tell you it's red, that means I only care about the red cards. So how many out of the 52 cards are red? 26, half of them. All right? And if I tell you it's red, what's the likelihood that it's also a heart? See what I did there? Okay? Well, I have to ask you, if I tell you it's red, out of those red cards, those 26 red ones, how many are hearts? 13. So this one is a lot easier to see. It is 0.5. So you've got a 1 out of 2 chance that if I tell you it's red, that it's also going to be a heart. Now, here we go. It's my favorite one. What's the probability? I tell you it's a heart. I tell you it's a heart. So how many hearts are there? 13 hearts. And then what's the probability that it's also red? And Charlize, you just figured it out. All of my hearts are red. So the answer is 1 or 100%. If I tell you it's a heart, and then I say, well, what's the likelihood that it's also red? I know it's red because all the hearts are red. All right? Just keep it going. We're good. We'll keep it going. Watch it this weekend. All right. Number 4. Are red card and spade independent? All right, now watch this process because you have to do this for a quiz on Wednesday next week. All right? All right, let's see. Wednesdays, pick one. You want to pick red card or spade? Red card. All right, let's find the probability that we get a red card. Okay? Out of 52 cards, what's the likelihood that it's red? 26. So 0.5. Okay? Now watch this. Okay? This is where it gets a little confusing. I'm going to find the same probability, but a little different, because now I'm going to tell you that the card is already a spade. So hold on, I want to make sure your brain sees it, okay? So which one did Wences pick? He picked red. So I found a probability for a red card. Then rewrite it, but this time you have a condition, and the condition is the other event. So just kind of make sure that mental note happens when you're doing this, okay? So how many spades are there? There are 13 spades. And how many of those are red? 0. So now it went to 0. So if they're independent, if these two events are independent, what should you see at the end? What should you see at the end? No, what should you see at the end? The same number. If they're independent, if I tell you something else happened, Saul, if they're independent and I tell you something else happened, then it should be the same, right? Because they would have no bearing on the other one. They'd have to be the same. So are they the same? No, and more importantly, they're not just not the same. So definitely not independent. But one went to 0. We can't have red spades. So these are actually disjoint. They're disjoint. They're mutually exclusive. There are no red spades that exist. All right. We got 2 more. We can do this. Number 5. Are red card and ace independent? Guillermo, pick one. Red or ace? Ace. Okay. Out of 52 cards, how many are aces? No, 4. There's only 4 aces, right? So that's 1/13. All right, whatever that is, the decimal. Don't care. So I'm going to rewrite ace, but now what's my condition?
Red.
My condition, yes, is that it's red, the other one. So how many red cards are there? There are actually 26 red cards. And out of those 26 red cards, how many are aces? There's 2, the ace of hearts and the ace of diamonds. And oh my goodness! They're the same thing. So that means they're independent. Let's stay.
No, actually.
No, we're doing one more, Jarvis.
Yes.
The last one. The last one. Jarvis, pick one. Face card or king? All right, so face card. Face. How many cards are there? 52. Let's make sure we know the face cards. Face cards are jacks, queens, and kings. So that's 3 sets. And there's 4 of each of them. So 4 times 3 is 12. So whatever that is. All right. Now I rewrite face. Given. It's a king. All right. How many kings are there? There are 4 kings. Out of those 4 kings, how many are face cards? All of them are face cards, so this is 1. Are those the same number? No. Did one go to 0? No. So they're not independent. No. And they're not disjoint. Neither.
Dang.
Whoa.
That
Eyeball.